Uh, a very good morning, all of you. I'm not from a dental background, as you see from my introduction. Anyway, I work on materials processing, producing different type of materials using different routes. Obviously, recently I started working on high entropy alloys, which may be promising to be used as a dental materials. So that's why how I connect to this particular conference. So I come from presently I'm working in Malaviya National Institute of Technology in the Department of Metallurgical Materials Engineering. This is my institute. It's spread over 300 odd acres, and it has been established in 1963. So this is regarding like my institute, and it's an institute of national importance of our country. And the Department of Metallurgical Engineering works on different materials, composite materials, polymers, and especially metallic materials, alloys, and their production, characterization to be used in different applications. So high entropy alloys. High entropy, see, there's a difference. What an alloy and a metal. A metal, obviously, metallic material is different. It is metallic materials are different from like ceramics, composite materials. Metallic metals having special, their special category because they do have a good conductivity, electrical conductivity, thermal conductivity, and processability. Processability means they should be shaped. See, we speak about a lot of things like to be used in different applications. It becomes very important to be, we can use the material only when it is in some form. For example, in dental application, wires you need. Some bioimplants you need some screw type of shapes. So all these shapes made of some material should be first produced in that shape, and then the important thing is for that application what is the need. In some applications, suppose aerospace materials, they need a lightweight material, and it should be there should be resistance to high temperatures, thermal shock resistance, and corrosion resistance, a lot of things. Aerospace, obviously, they should be lightweight. Automobiles, same, depending on the application where you use, they have certain things to be considered. In the case of bioimplants, for example, dental materials, a lot of things like whenever we use a material which can be used in our body, they should be biocompatible. Corrosion resistance should be there. They should be biocompatible with respect to different type of conditions in our body fluids. So all these things. So these materials, first thing is shaping, to produce in that particular shape to be used, and the material should be perfect in that application with respect to all these properties. It should be amenable to the situation. So high entropy alloys are those alloys in which we use different elements, approximately 5 in equal atomic compositions. And the speciality of these materials is they have high degree of randomness. Entropy means disorder. Entropy means higher, it's a disorder, it's a measure of disorder. So these alloys will have a special consideration in which we can be used. There is no single phase. There will be, it will be having a single phase. For example, I'll just introduce before going one thing. The difference between a composition. For example, everybody knows about steel. Steel is an alloy of carbon and iron. That means it is an interstitial solid solution of carbon in iron. Okay, so that is an alloy. In this, for example, there are more than 2,000 varieties of steels used in market for different applications, depending on the considerations which just I spoke. So, for example, 0.1, 0.2% or 0.2% carbon steel if I take. That will be having good ductility, processability, and it's okay. Okay. Is my voice too loud? Yeah, sorry. Because I thought it's okay. Okay, we're speaking about steel. So 0.1%, 0.2% carbon steel. So if I take 0.2% carbon with the iron, we'll have in that particular composition you form different phases. For example, cementite, alpha ferrite. These two are phases which formed at room temperature. So these two are phases. Each phase is having its crystal structure different. They behave differently because they will be having different properties with respect to all these things. So a solid solution, what in this case, if we use 5 different elements in equiatomic composition, we produce a solid solution, a single phase, which is having this property of a high randomness, which can be used in different applications. Especially this type of composition will be having high corrosion resistance and good biocompatibility. But it's anyway, this is being thought like that in future prospects. This will be these particular materials will be promising. So one more thing, like producing of ultra fine and nano materials of this sort becomes very important because the processing temperatures will be less. I can produce these shapes at lower temperatures. That is the only essence of producing this ultra fine and nano structured materials. Anyway, this categorization, I think everybody knows. The nanomaterials are materials which are having the components in their in the size range between 1 to 100 nanometers. And here we speak about submicrocrystalline and ultra fine grain sized. Nanostructured means the bulk material. There is a difference between a bulk consolidated. Bulk consolidated means a material which can be used, which can be processed in a bulk form, solid form. It is having particle bonding or metallic bonding in the case of metals is called a bulk material. And the nanostructured bulk materials or consolidated materials having grain sizes. The grain size will be in that particular range. See, production of materials, metallic alloys and metallic materials can be done by using 2 methods. One is ingot metallurgy, that is I melt a metal, for example aluminum alloys or titanium alloys, steel, anything. The thing is we'll melt at high temperatures and then we'll be either casting it or doing some processing to shape the materials. That is one type of thing which will be used to produce some material. And second thing is powder metallurgy route. Powder metallurgy route means the starting materials are powders. For example, titanium based material I am producing for some application. Example, dental application or aerospace application, wherever it is. We take either pre-alloyed powder or elemental powders we mix up and then we'll be processing it high temperatures to produce a bulk material. See, why powder metallurgy? Powder metallurgy alternative economical viable mass production method for producing structural components. And here the main significance of this powder metallurgy route is it can produce a near net shape. Net shape means there will be no finishing and machining operations. Directly it will produce the shape. For example, in some case I need to use a biomaterial in a screw form, in a bolt form, in a rod form. So that can be produced without any further direct that material shape you'll be getting with this particular method. Net shape and near net shape is the significance of this particular process. This is the basic of this powder metallurgy. So what initial powders will be compacted into green compact. It's general method. They do in some cases they do directly go take the powders. They will be rolling it. They will be forging it. Advanced techniques. But in general, fundamental basic thing what they do is the powders will be initially converted into green compact. Green compact is that compact in which there is no interparticle bonding, only because handling the powders will be difficult. We will be compressing the powders to produce some material to handle, to make handling easy, and further it will be sintered. Sintering is the impartition of a interparticle bonding between the particles. So that is how we will produce a bulk material. See, producing this particular bulk material is important, because without this, in this form, we can't process it. If you process it, this will be, because there is no interparticle bonding, it will break. So what is the significance of producing this nanostructured powders? Nanostructured powders, because if we, as I told, what happens is, if we are able to keep the grain sizes at lower than very low grain sizes of bulk material, the benefit is you can process the material at lower temperatures, because processing means shaping the material is not easy. As we said, we are getting every shapes, we are enjoying different type of materials in automobiles, aerospace, bioimplants, but it's very difficult to produce those materials with respect to shape and with respect to properties needed. So as we go higher temperatures, what happens? It's very difficult to control. In some cases, you need a 1000 degrees centigrade processing temperature to process the material. So producing this powders, what happens is it reduces the processing temperature to much lower temperature. For example, in some cases 900 degrees centigrade with respect to the coarse-grained counterparts. And in the case of nano and submicrocrystalline grain size materials, what happens is the temperature will be reduced to, it can be processed at 700 degrees centigrade. What happens is it reduces the brittle to ductile transition temperature. Because of that, the processing will be amenable. That is why it is beneficial to produce these powders, and further it can be consolidated so that the grain sizes will be in control. So later on will be, that is what's a consolidation and of these powders in thermomechanical techniques. That is what you do. This is a typical like flow chart for powder metallurgical processing. Elemental powders, I can use elemental powder. Elemental powders means in the case of some alloy, the same thing, which same example I'll take. For example, steel I am producing 0.2%. So carbon I'll take in that particular composition. Iron I'll be taking separately. I'll be mixing, and then cold compaction. Then further to improve the density, I'll do cold isostatic pressing to produce a green compact, and then I'll be doing a thermomechanical consolidation technique. Further multiple processing to get the shape needed to be used in certain applications. In the case of pre-alloy, other thing is pre-alloyed powders. I can directly get the powders, pre-alloyed powders. Alloyed, it's already alloyed. So each particle will having a certain composition. So that will be just mixed, because already it is an alloy, and then the same processing will be done to produce the material. Milling is a technique by which you do this. Here it's mentioned, mixing and milling. It will be done in a ball mill. It's a planetary ball mill. So the milling can be done in two ways: wet milling, dry milling. Wet milling, organic surfactant will be used to avoid, because whenever powders will be used, you should be very careful. As the surface area reduces, reactivity increases. Obviously, when it becomes oxidizes, the material is of no use, because it can't be used anywhere. So wet milling use a PCA, which is process control agent toluene. It controls the milling process, one by increasing the efficiency of the process. Second thing is it also avoids the oxidation. In the case of dye milling, you will be using a stearic acid as a process control agent. This here sticking tendency will be slightly higher, because ball milling imparts a lot of energy to the powders for the reduction of size for the alloying purpose. So because of that, because there is no liquid medium in it, there is more chance of a sticking of the powders. So this is the typical ball mill in which you process the powders. This is a planetary model. Planetary means obviously it is based on, it is called planetary mill because it is based on planetary motion. Planetary motion, rotate, revolve. So that is what is happening. Rotates, this particular wheel will rotate, and this particular wheel will rotate and revolve. Because of that, and there will, this is what happens, these are the balls and these are the powders. So there is a impact force, different type of forces which will be imparted. There is a transfer of energy from the balls to the powders, which makes two things. One is reduction of size, and second one is it makes the mechanical alloying process successful. This is the mechanical, mechanism of milling. What happens? The milling action will be in this milling action. There is different types of forces which are involved: shear forces, frictional forces, and impact forces. Because of that, what happens? There is a transfer of energy. There is a transfer of energy from the balls to powders. So this is what is the general scenario of this. The sticking, less sticking in the case of wet milling, and more sticking in the case of dry milling. So it should be careful to maintain the composition. What happens? It should be very careful while using the dry milling, because sticking deviates from the composition. So these are the ways to synthesize nanostructured powders. Initially at lower RPM will go in the case of binary and ternary compositions. Will ensure the homogenization, and then in some cases you go for a nano composite powders. In some cases you go for a alloy powders. These are the parameters of mill, because all this ball to powder ratio, ball diameter, ball material, all this becomes very important. Ball to powder ratio, the energy transfer depends on the RPM, the speed of rotation, and the type of ball material, type of the wire metal used becomes very important. We have done this milling of the powders of particular composition. So what we found is we were successful to produce a single phase of solid solution. In this case, that means high entropy composition has been composition of this alloy has been successfully formed. So this can be used further. We need to produce it into bulk form to see the properties, whether it can be used in different applications, in aerospace, in automobile, and especially in even dental applications. Differential scanning calorimetry studies also confirms the melting point of the particular material at the same time. So to convert this particular material into bulk form, we will be using like different techniques. These are the different type of thermomechanical consolidation techniques: hot pressing, powder compact extrusion, powder compact forging, hot press, it is repeated. So powder injection molding, hot isostatic pressing, equal channel angular pressing, etc. So this is the typical process used for HIP. HIP is nothing but hot isostatic pressing done at higher temperatures to produce a bulk material. Degassing becomes very important in this, because any amount of gas, regardless of nitrogen, carbon, oxygen, will devastate the material. Should be very careful. So these are the typical things for bulk material produced of different composition based for aerospace material of titanium composition, which is produced in a lab. And this is one more different shape produced. Further, this should be processed into some shapes. So using powder compact forging, we used also titanium based material in this, with uncanned and canned forges with uncanned forging. So this is what I told: reduce brittle transition temperature. They can be hot worked at lower temperature. That is what, reducing this particular temperature, the BDTT will be coming down, so that we can process at lower temperatures. So that in some cases superplastic deformation also is amenable, can be done to produce net and near net shapes. So these are typical components which are produced. Anyway, in concluding remarks on future works. Future work means, in the case of high entropy compositions, we need to produce further materials like bulk material. It's in process, bulk material in process, and shaping also we need to do, so that it can be used in certain applications, different diverse applications. Initially, I worked on this automobile applications in aerospace mainly. And recently, from last 1 year, I am concentrating on high entropy alloys, which are promising in dental applications. Anyway, thank you. I acknowledge my colleagues, my PhD students for the support they have given, and obviously my family members for all these things, and even my superiors. Thanks a lot for listening patiently.